Hello friends, in this video today we are going to discuss about law of variation of mass, and we are also going to discuss about Einstein mass energy relation. Let us assume that we have two frame of references. This is one. This is, suppose, let me write only two axes. So this is S and X, this is Y axis, and another frame of reference, suppose S dash. This is S dash, and here it is X dash and Y dash. These are the two axes, and let it be moving with velocity v with respect to it is moving with velocity capital V with respect to this frame of references. Okay, this frame of reference S dash is in motion, and whereas S is at rest. So now let us assume that we have two objects A and B, and in this frame of reference S dash, and they are moving with velocity equal velocities, and they are suppose v1 and v2, small v1 and small v2 towards each other. So let us suppose that v1 is equal to minus v2. They are opposite in sign but equal in magnitude. Okay. So there must be m1 and m2, and they're moving towards each other in this frame as this. Now here you see, by the law of conservation of momentum, by conservation law of momentum, we get that m1 small v1 plus m2 small v2 is equal to, now you see, after collision, suppose they stick together and move as a single object of mass m1 plus m2 with velocity capital V with respect to the frame of reference as this. Then before collision and after collision, total momentum conserved. That's why we will get m1 plus m2 into V. And this is suppose equation number 1. Let us suppose this is equation number 1. Now by the law of addition of relative velocities, relativistic law of velocities, addition of velocities, we can write that this velocity u1, it is with respect to s dash, isn't it, in this frame. So what will be its value with respect to this frame of reference s? So that's gonna be, now because here you see these two are moving towards each other with velocities v, small v1 and small u1 in this frame of reference s dash, in this frame of reference s dash, but again this frame of reference is also moving with velocity capital V. That's why relativistic velocity will be small v1. That's going to be equal to, if we consider that magnitude of these two velocities, small v1 and small v2, be suppose u, these two magnitudes of these two be u. In that case we can write u, sorry, not u, let me consider only v, small v. Okay, let me consider as small v, then small v plus capital V. Capital V is the velocity of this frame of reference with which of this frame of reference s dash. This is moving with velocity v, isn't it, capital V. And this is the frame of reference s dash. It is moving in this direction, x-axis, along x-axis, isn't it? with this velocity capital V. This is capital V and this is small v divided by 1 plus small n capital V by c square. And similarly, let me scroll down the page. V small v2, that's going to be equal to small v plus capital V. Here in this case, this one will be minus, as a small v1 and small v2, they are equal but opposite in sign. That's why if their magnitudes small v only, then one is small v, another must be negative small v. So that's why it is negative. So 1 minus small v and capital V by c square, we have got this. So let us consider that this pair of equations be equation number 2. Okay, let us consider this pair of equations as equation number 2. Now use this equation number 2 in equation number 1. So here you can replace this, here you see you can replace this v1 and v2 respectively by these two values. And if you do so, then what you will get, using 2 in 1, then what you will get, if you replace this small v1 and small v2 by these two values of small v1 and v2, then you will get m1 into small v plus capital V by 1 plus small v capital V by c square plus m2 minus small v plus capital V by 1 minus small v capital V by c square is equal to small m1 capital V plus m2 capital V. So hope you have understood this. What we have done, we have used equation number 2 in equation number 1. This is equation number 1. So that's what we have got. So now if you simplify this, after simplification, if you arrange this equation such that and term consisting m1 are on left side and m2 are on right side, then after taking the common terms m1, then we will get small v plus capital V minus v capital V minus small v capital V square by c square by 1 plus small v capital V by c square. On the other side of this equation will be m2, here capital V minus small v by capital V into capital V square by c square plus small v minus capital V, so divided by 1 minus small v into capital V by c square. So here let me write this as small v properly. Okay, this is small v. Okay, so now here you see this 2 will be cancelled, here these 2 will be also cancelled. So then what we will get after simplification, here we will get that m1 by m2. If you find m1 by m2, then what you will get, as a numerator you will get small v into 1 minus capital V square by c square divided by 1 minus small v capital V by c square, whole thing divided by small v 1 minus capital V square by c square by 1 plus small v capital V by c square. So here you see, so what we can do here, we can cancel these two terms, and so here you see after simplification this term will be here and this term will be here. So finally we have got m1 by m2 is equal to m1 by m2 is equal to 1 plus small v capital V by c square by 1 minus small v into capital V by c square. And this is suppose equation number 3. Let us give this as equation number 3. Okay, so now what we are going to do, so here you see let us find here you say this from this case what we are going to do. Now let us find, now first let us find 1 minus small u1 square by c square, because we are going to relate this with small v1 and small v2, so that's why let us find this. First, if you replace the small v1 by the relativistic velocity, then what you will get here 1 minus, so small v1 will be small v plus capital V by 1 plus v by c small v into small v into capital V by c square we get, isn't it? So let me write it clearly. Okay, so what we have got here, 1 plus small v into capital V by c square, that is what we have got after replacing small v1 by the relativistic velocity. Here it will be c square, and after simplification, if you simplify this, then you will get 1 minus small v1 square by c square, that's equal to 1 minus small v square by c square into 1 minus capital V square by c square divided by 1 plus small v capital V by c square whole square. That's what we will get. That will be equation number 4. So similarly we can find 1 minus small v2 square by c2 square. So here it will be 1 minus small v square by c square into 1 minus capital V square by c square whole thing divided by 1 minus small v into capital V by c square and whole square. That's what you will get. Now this is suppose equation number 5. So this is, now here you see, if you divide these two equations, if you divide equation number 5 by 4, then what you will get, then you see here these two terms will be cancelled, these two will be cancelled. So if you divide by 4, dividing 5 by equation number 4, so we're gonna have that 1 minus v2 small v2 square by c square divided by 1 minus small v1 square by c square, that's going to be equal to 1 plus small v into capital V by c square whole square and 1 minus small v capital V by c square whole square. So we get this. Now you see, if you see the equation number 3, if you see this equation number 3, here m1 by m2, this is equal to 1 plus, here you see this right hand side same as this one, but here only we have squares. Okay, so that's why this right hand side can be replaced by m1 by m2 whole square. So if you do so, then what you will get, then you will get that m1 by m2 whole square is equal to 1 minus v2 square small v2 square by c square by 1 minus small v1 square by c square, and if you remove the square, or you can take square root on both sides, then what you will get, m1 by m2 is equal to root over 1 minus small v2 square by c square by root over 1 minus small v1 square by c square. That's what we have got, and it implies that m1 into 1 minus small v1 square by c square is equal to m2 into root over 1 minus small v2 square by c square, and that's equal to suppose m naught. Let us consider it is suppose m naught, and this is known as rest mass. In this case it is known as rest mass. So I hope you know the concept of rest mass. Now if you consider that both the particles are both of them are moving with both the two bodies A and B moving with the same velocity and they are of same mass, or you can consider the system of one particle, then you can write this expression in this way: m is equal to root over 1 minus v square 1 minus v square by c square. Sorry, this is m naught, small m into this. Okay, we can write this way, or this implies m is equal to m naught by root over 1 minus v small v square by c square. So let me write it properly: v square by c square. So this is what? This is our law of variation of mass. This is the law of variation of mass. Law of variation of mass. Now this is suppose equation number 6, and using this equation again we can find we can derive the Einstein mass energy relation. How to do that? We know that force F, it is the rate of change of momentum, that's why d by dt of mass into velocity. So now if you consider m and v both as variable, okay, m and v is both variable, because here you see generally we used to consider mass is constant, but here you see as we are going to use the law of variation of mass, we will consider here mass is mass and velocity both are as variable. And now use the product rule of derivative, that we know u into v, its derivative is given by u, then derivative of v minus v derivative of u. We know that if you use that rule, then you will get f is equal to m dv by dt plus v dm by dt. So we know energy energy is given by force into displacement, so f of dx, f into dx. So here, so f into dx is equal to m v dt plus v dm dt to dx. As we know that v is nothing but dx by dt, so from here dx by dt, here we from here we will get v, and so v square, again dx will be multiplied here, then dx by dt will be again v, then yes, and then we will get here m v dv. So that's why this equation is going to be equal to f dx is equal to m v dv plus m v dv plus v square dm. We get this. So now force into displacement, this is nothing but energy, so dE we can write m v dv plus v square dm. So this is suppose equation number 7. This is equation number 7. So what we're going to do here now, if you now take the equation number 6, if you square both right and left hand side of this equation number 6, so squaring the equation number 6, then what you will get, you will get that m square into 1 minus v square by c square is equal to m naught square. From equation number 1 you will get this, okay, after simplification. And that implies before that now let us differentiate this. Differentiating, so differentiating it, we get twice m dm minus 1 by c square d m square v square minus m square. So here v square minus m square 2v dv is equal to 0. Here m naught is constant, so m naught is constant, so I have done a mistake here. So what is that? So that's gonna be equal to this one, sorry. So this is equal to 0. Here m naught is constant, okay. Now here we are going to use the product rule of differentiation again. Then we will get twice m dm minus 1 by c square and what you will get, so twice m v square dm minus m square by c square 2v dv is equal to 0. So multiplying both sides by c square and dividing by 2, that means we are going to multiply this this equation by this term c square by 2. If you do so, then what you will get? Then you will get that dm c square is equal to dmc square. Also we are going to divide each term by m as well, because here you see they all consist m, here, and this is m square. So then we get is equal to v square dm square plus m b dv. And here you see this term, in this case this term is nothing but this is equal to this right hand side of equation number 7. So using 7 we can write, if you use equation number 7 here, then you can write that de is equal to dmc square using 7. Now what we are going to do, we are going to integrate this. If you integrate this, then you will get e is equal to mc square equal to mc square. That's what Einstein, that is the Einstein mass energy relation. Einstein mass energy relation. So hope you have understood. So if you think it is helpful for you, then please share with your friends, and if you are new to my channel, subscribe the channel and help me to grow my channel. Thank you.